The second part of the first practice test begins with a question really from chapter 11. Now, at first glance, you might think this is a normal distribution question, but it's talking about simulations. Inside the simulations, we have the result here. We have a sample size of 1,000, and the question says, is the event of Audrey selling at least 7 of the 30 tickets is unlikely to have occurred by chance alone? Well, we can come up here. 7 or greater would fall into this situation right here, right?
What question are we on?
I'm on 21. Now, remember, if you're going to be looking at this question, number 21 comes really from chapter 11. Okay, this is where we learned about simulations. In this case, you're looking at 7 of 30, and they want to know, at an alpha level of 5%, is this unusual? What's the probability that I should see a sample like this, right? If the mean really is kind of what we assume it to be. And so in this case, you can count up. We're looking at 7 and greater. So that's really, if we add all this up, you're going to get 138 out of your 1,000 trials showed up to be this value, right? So we can have 0.138 or 13.8%, just under 14% of the time, we would expect to see something like this happen. And so that's not unusual. I mean, it's not going to happen all the time, but it's greater than 5%, right? So I'm definitely not going to reject my null in this case. And so is that unusual? You'd say no, it is not unusual. I can eliminate the yeses because 13.8% is definitely bigger than 5%. And so here, this question was no, and answer choice D doesn't make any sense. We don't always talk about the number of tickets, 0 to 11. But we did talk about that getting 7 to 30 tickets, which was the one we added up, would happen around, we would expect it to happen around 13.8% of the time. So that's that one. Number 22. This one comes from chapter 18. This is probably the easiest one of the whole test. This is a really simple one, a very big definition question. It's asking, of the 34,000 people who attend the university, in other words, everyone at the university, and it says, of the 770 students selected, 493 students indicated blah, 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 whatever. The question was, what's the population? What's the sample? Well, the 34,000 was everybody, and the 770 is the sample. Does that make sense? I mean, it kind of tells us, of the 770 students selected, a sample is the number of people selected from the population. The population I picked it from was the students that go to the university. Since there's 34,000 people at the university, then answer choice D makes the most sense here. Number 23, this one was where, if you read the question, you have a group of 40 men, and they have their blood pressure taken, then you're given medication, and then they have their blood pressure taken again. I can go ahead and I can mark off the 1 proportion or 2 proportion and chi-square tests. This is a quantitative test. Blood pressure has a quantitative measure, so it is not categorical. The question is it matched or is it paired? Or is it just 2-sample test? We know it's 2-sample test because one group of individuals was given both sets of data. Okay, or you could say, is there a natural pairing between the two, right? It's a pre and a post test. It makes a lot of sense that it is a matched test, not a 2-sample individual independent test. That would be from chapter 25. Number 24. In this question, we are looking at the first thing you should recognize is that it's got linear regression information, right? So this is from chapter 7 to 9. We know that this value here is our y-intercept. We have this value here, which is our slope. So creating the line of best fit would be really simple. You're just basically going to take that information and put it into the formula that we've used all this time with linreg. It's asking us based on the residual, right? So residual is equal to the observed minus the predicted. So two formulas that I need to remember. Now, the y hat is technically on your formula sheet, but you may not know how to use it. Okay? Make sure that you find that it's usually, sometimes it's called y hat, sometimes it says b0 equals and stuff like that. Those little three formulas I always reminded you about. Okay? The question was, is the residual overestimating? Is it underestimating, is my prediction? And is the residual positive or negative? So I guess we need to find out what the actual residual is. We have the observed value of 59, right? So observed is equal to 59. No, sorry. The observed is 31.1. We can find our predicted value, right? The predicted, remember this is your y hat, is equal to negative 1.281 plus 0.5. Oops, not parentheses, 5264 times, we're going to go ahead and plug in our original x, 59. This is going to give us a value of 29.78. We predict the tail length, we predict the total length to be 29, what is it, tail length, yeah. We're predicting the tail length to be 29.78 centimeters long. The actual value was 31.1. So we're going to use our residual is equal to 31.1 minus 29.78. This is going to give us a residual value of 1.32. My residual is positive, so I can mark off 1, 2, 3 values. The question is that over or underestimating? I always got this backwards. I always have to draw a picture, right? If I have a point here and a line there, then my line is my estimate, right? So this is going to be y. This is my observed. This is your y hat. It's always observed minus predicted. This would end up, this scenario I'm drawing right here is underestimating. And I have a positive residual that results in that. So we are underestimating the value. So A would be the choice for that one. Okay, 25. This was a really simple question. This is just normal CDF. Okay, it tells you between 4 and 5. So 4 is your lower, 5 is your upper. 4.5 is the mean, and 0.6 is your standard deviation, and you're going to get 0.5888, which is approximately 59%. That one, there's not a lot for that I can really argue with you about. That's how it is, right? Hopefully we got that one right. The majority of students did get that one right. 26. This one required you to read a little bit. Essentially, once I get through this, you're going to find out this is a one prop z situation. In this case, they're talking about one prop z test, because you're talking about a significance test. Using an alpha level of 5%. If you read that last statement, what am I trying to show? That's going to give me my alternative hypothesis, right? So HO and HA are going to be important to note here. If I get this wrong, I'm definitely not going to get the correct p-value. The good news is the p-value that I would get would be very large. And so I would have a pretty good indication that I'm doing it wrong, because none of my p-values work out to be that. But it tells you that p is greater than 0.03. You're trying to show that more than 3% are produced that are overweight, or they're underweight. And so my null would just be that they're equal to 0.03, which that implies the null is also that it's underweight. If I take that, run that in, I've got x is equal to 40. My sample size was 1,000. That's exactly what I needed to know in order to run that test. I'm using an alpha level of 0.05. It turns out that you're going to get answer choice B, p-value of 0.032, which definitely is less than my significance level. We definitely would reject the null here. 27. In question 27, this is about the central limit theorem. This is chapter 18. In chapter 18, we talked about what happens as you increase sample size, what happens to variability. We know that a sample mean, when you create sample means, is when you start to increase that sample size, variability spread shrinks. So if we're going to go from smallest to largest, graph A has the largest range. Therefore, it has the largest variability. It has the smallest sample size. Then you would go, C would be next, and then graph B would be third. So you're going to get A, C, and B as the order from smallest sample size to largest sample size, which gives you answer choice A. All right, number 28. This one comes from chapter 13. This is about experimental design. Things I want to remind you about. In an experiment, we're looking for randomization, right? We're looking for replication and control. If we can establish that these three elements, blocking if it's necessary, this one didn't have anything to do with blocking. If we can establish that these are done well enough, then we can establish that a cause and effect response is warranted, right? So if I read the question, you have 40 adults that were asked to drink a liter of water each day and not to consume any other soft drinks. Okay, the other 40 were randomly assigned to consume 1 liter of soft drink a day. So we're clearly here and we're getting an experiment. We have manipulated variables, right? Which means I have control in effect. They also told me that they randomly assigned them to 2 groups. They also put more than 1 person in each group. So it is replicated 40 times over for each of the different treatments, right? So I'm not just doing it one time and I get this really crazy response, right? If that's the case, that variability is going to go way down once you can kind of see what everybody does all together. And so you'll get a good response. So it's an experiment. So I'm going to go ahead, I'm just going to mark off D and E because they're talking about, no, you can't do cause and effect here. But I can. It's an experiment. That's the whole point of an experiment, right? And so if I look at it, it says that the average was higher in the people who drank soft drinks, right? So I'm looking at the conclusion there. It says the group of people who drank soft drinks had a higher storage of fat in their tissue than people who drink water. So what conclusion would you make if that was what you got out of your experiment? Well, answer would be C. It seems like there is evidence that drinking soft drinks can cause more fat to be stored in the people that were in the actual experiment. Could I investigate? Could I imply this that goes to the whole population? I don't know. I could. It's only about who's in the actual sample.
So also they were volunteers. They weren't necessarily random select.
Right. I don't know that this group of people, especially 40, represents all adults, period. That seems like a really shallow, and like you said, I didn't have any control over who volunteered. I just had control over who went into which group. So that's a big deal. Okay. Number 29. This question, this is from chapter 19. We are looking at a 1 prop z interval. Specifically, we're looking at how it's composed, which we have our p hat plus and minus the critical value times the standard error, which is p hat times q hat over n. Now there's a number of ways to do this. There's a kind of a direct route and a route that if you know a little bit more information, you can take the shortcut. Okay, so I'm going to kind of go through both. In this example, it's asking us to talk about the very supportive or somewhat supportive. That's important. Where that puts us in these two groups. If we think about that, it's disjointed. I can add those probabilities together. And so what you'll end up with is 336 plus 387 to give you a total of 723. That's out of your 1,018 total responses. And so this is really equal to my p hat. Turns out that that's equal to 0.71. So instantly I can eliminate two of my answer choices, right? P hat is 0.71. I can also calculate the margin of error. I have sample size is 1,008. I have my p hat is 0.71. Obviously Q is going to be 0.29. But my critical value, well, what's my critical value here? It's 95%. It's 1.96, yeah. Now they didn't list that out, right? I can't see that because they multiplied it all together. So this part is your margin of error. However, if you take it for a minute, if I did a 1 prop z interval using this information, right? It's going to be x is equal to 723, n is equal to 1,018, and your confidence level is equal to 0.95. You're going to get this interval, 0.68235, up to 0.73808. What do you know about the interval itself? If I were to subtract these two numbers and divide by 2, what do you get? If you do 0.73808, yes. If I subtract these two values, 68235, and that's equal to 0.05573. If I divide that by 2, I get the margin of error, which is equal to 0.028. Okay, it rounds to 0.028.
So is that the only way to solve it? To find
No, I could go ahead, I could use my formula. I could have done it up here. Go directly to the formula, 1.96 times the square root of 0.71 times 0.29 divided by the square root of, or by 1,018, then square root it all. That's still going to get you 0.028. But if I'm trying to do this the easiest way, I'm going to go in and I'm going to create this interval. I'm going to go in, I'm going to find the interval, subtract the 2, divide it by 2, I'm going to get the margin of error. Notice up here, there's only 1.028. Now that's 0.029 is close. If I had to choose between the two, I'm going to go ahead and find p hat 2. If you add these two numbers and divide by 2, you get p hat. That gives us the other one. So I can use the formula direct like I started to here, or I can use the interval, add, subtract, divide by 2, if I have the center, the p hat, as well as the margin of error. So kind of up to you how you wanted to do that. Okay, number 30. Number 30 is from chapter 18. This is the central limit theorem. This is like the pennies, the nickels, the dimes, and the quarters, what we talked about. The central limit theorem is all about sample means, right? The nickels, the dimes, and the quarters we put on the floor all were representative of averages. And so when it talks about, in part A, the number, A, B, and C, it says the distribution of the number of recharge cycles. No. We want to talk about the sample means of my distribution. And so that leaves D and E as the only possible choices, right? And it says the distribution of the sample means of the number of recharge cycles is approximately normal because the sample size of 100 is greater than 30. Or it's normal because the population mean of 400 is greater than 30. Which one do we talk about being large enough to consider it approximately normal? Is it sample size or is it population average? It's clearly sample size, right? We don't ever talk about population mean being anything. So, central limit theorem says as long as you have a sample size of at least 30, then you can expect your distribution to be approximately normally distributed. Number 31. This one is looking at a 1 prop z as well. This was from chapter 19. This one was about the 1 prop z interval specifically. And the easy way here, I'm talking about 90%. We know that the critical value for a 90% confidence interval is equal to 1.645. So I can instantly lose it down or remove it down to 2 choices. If you haven't noticed, each time I try to eliminate some of the more outrageous answers that we know can't be the answer. I need a way to determine that, and each question has its own set of rules, right? In this case, it was easy to see the critical value out in front. That was easy for me to fix. Okay, 1.645 was the one. Now I look at the remaining choices and I see what's the difference? How can I know which one's which? Well, the number up inside that radical is p hat. Unless I don't know p hat, and then I have to use 0.5. The question is, did they give you the proportion of the sample that represented? Is that 16.2%, or do I not know that number at all? Well, that's exactly what it gives you here. 16.2% of the adults recorded in the sample, so I'm done. It's A. They gave me p hat, so I'm going to use p hat. Any questions? Okay, let's move on to 32. This one is tricky. At first glance, when I first read this question, I thought it was a slam dunk. This is a matched pairs t-test, but there was a word in the paragraph that made me think twice. What word do you think that is? Anybody want to guess? What word would make me think twice about using my matched pairs test for this?
Random?
Random is important for all. Thank you. You see that word right there? Predict. That made me pause. I'm like, wait a minute. That seems out of place in my mind right now. We don't predict using. Yes, ma'am.
That's not on the question.
Yeah.
Is that whole paragraph missing?
Yeah.
Yeah.
It's on.
It's just the top part and the chart and then the answers.
Okay, I'll look at it. I must have.
Wait, you're kidding.
Yeah.
So if that paragraph's missing, I'll give credit for both answers. Okay. If you didn't know that paragraph, if you didn't see that, then a matched pairs test would have been absolutely the choice to go with. Okay.
I put matched pairs teachers.
Let's go.
Now, it's before and after. That's your clue. That was my first thought. But when you read the paragraph, I want to predict with this. Could I create a line of best fit? Could I use the before score to predict their after score? The answer is, do I have one individual with 2 sets of data? I do. I can definitely create a line of best fit here. I can definitely try to predict before scores with after scores, or predict after scores with your before. And so because it talked about predicting here, well, first of all, it's quantitative. And so it was either going to be matched pairs or lin-reg. I guess you could have also talked about it being this too, but it's predicting. So I'm going to use one to predict the other. That always falls into your linear regression t-test. So that would fall into chapter 27. Okay. 33. This question was asking you to interpret a confidence interval. This really comes from chapter 19, where we first learned about confidence intervals and things. They tell you that you have 19% is your center, and that there was a margin of error of 1%, right? So your interval would have been 19 plus or minus 1. So we're really looking at 18 to 20%. If you read through your answer choices here, okay, the 1%, the margin of error, isn't about the number of people surveyed. So I can mark off A and B. Those numbers don't really matter. They don't make any sense. C could potentially be a possible answer. It says all possible samples of the same size result in 18 to 20% of those who surveyed, indicating they were using sunscreen regularly. But that is incorrect. There is nothing special about your numbers, your interval, that would ever be repeated. Lots of people may redo this, but they're going to get slightly different intervals. It also, all possible samples of the same size, I have no idea what's going to happen, right? It's not about, I'm going to talk about the population would have something happen, not the samples, okay? D's trying to use the 1% as a probability, and that is absolutely wrong. E is the only one that makes any sense here. We think the true proportion falls in between 18 and 20%. So could it be 18.5%? Yes, that makes a lot of sense. I think it's between 18 and 20. You say, I think it's 18.5. I would have to say that that sounds like a reasonable prediction for what you think the true proportion really is, right? A plausible response. Not to mention none of the other answers actually make any sense. Okay, number 34. This one is specifically dealing with a single t-test. However, it's talking about interpreting the confidence, the significance value, the p-value. And so I can really find a lot of discussion on the p-value and interpreting it in chapter 21. So I don't care which one you throw it under, but I would need to be really, well, it doesn't matter. You can pick 21 or 23. In 34, it's talking about we had a p-value of 0.025. So I'm definitely going to fail to reject your null, right? It is not significant. And so I can go ahead, there is convincing evidence. No, there's not. I can mark off A, B, and C from the beginning because I would fail to reject the null, which means I don't have statistically significant results. So the difference here is that it's talking about all customers, or is it talking about the samples that we would get it? When you write out your conclusions for confidence intervals or significance tests, who should they be describing? The sample or the population?
The population.
Clearly the population. I know everything there is to know about that sample. I don't need to predict what I think is going to happen, right? So we're always going to go backwards and talk about that population value that has that we're inferring about. This question, this is one of those questions where there's a lot of work to do, but nothing was too crazy complicated. This is from chapter 6. Not anything really complicated. It was all about normal distributions. I gave you questions like this like 17 times, right? About using the z-score to get the standard deviation, to go back to normal CDF, all that jazz. The way we do this is that tell you that we would like to know what's the probability that the water will be at least 90 feet. So my ultimate goal is to be able to come in here with a curve. If I put, this is 0.9, this is 90 feet right here. What's the probability that it's above 90 feet? At least 90. Well, I need normal CDF to do that. So it'd be normal CDF. Right? I'm going to lower, that's easy 90, upper, that's easy 1E 99. Mean, okay, look, where's the mean at? They gave me that right there. So 84.07, and then standard deviation. Uh-oh. They don't give me that. So therein lies my first problem. I need standard deviation. Well, they also didn't give me much to figure out either, but they did give me this. We do know that 87.04 or 84.07 was here, and we know if at 100, the area past that is going to be 0.064, right? I know I need standard deviation. I know the formula, z equals x minus the mean divided by the standard deviation will get me that standard deviation that I need. And so if I were to plug in what I know, there's two things I don't know. I don't have a z-score either. That's okay, I know how to do that. Inverse norm. Well, down here, if we have an older calculator, this is going to be 0.936. If I have to use the area to the left, that's the older version. If I can choose the side of my area, if I have a newer calculator, then to the right side I can choose 0.064. To the left side it's going to be 0.936. I was using an older calculator, so I did it this way. 0 and 1, because that's going to give me a z-score, which turns out to be 1.522. That way I can come in over here back to my formula for my z-score. It's going to be 1.522 equals x. This case is 100 minus the mean, which is 84.07, divided by the standard deviation. Long story short, the standard deviation is equal to 10.4665. That was all I needed to go right in here. So 10.4, we'll say 7. That turns out to give me a p-value, or a probability of, where did I write it? 0.29. Okay, which turns out to be answer choice A. So a little bit of work, okay? Nothing crazy. 3 steps. I realized in normal CDF I couldn't do it because I needed standard deviation. So I went back and used the information they did give me, which means I needed to use a z-score. But I don't have the z-scores. I had to use the inverse norm to get the z-score from the percentile, then go back to the z-score formula, and then connect that to the normal CDF question, and then plug it in and work it out. Okay, good question. 36. This question is from chapter 23. In chapter 23, I have an alpha level of 5%. I have an interval right here. The president believes that the mean number of community service hours was different from 24. So he thinks it's not 24. If I look at my interval, I find that 24 is not in there. In fact, I think it's a lot less than 24. Or it's just less than 24. And so B describes the right answer. Some people may be tempted to answer choice A because we always talk about 0, but that's just saying, is there a difference in the two groups or the two numbers? In this case, I wasn't looking for a difference. I was comparing it to the number 24. 24 was not included in the interval, so I don't think that's a legitimate possibility. Okay. 37. 37 was legitimately, if you aren't good with combining multiple distributions, this one was fairly lengthy. You had to combine different results. We had 2 distributions, x and y. The mean for x was 0.36. The mean for y was 0.26. We had sample size for x, which was 60, and the sample size for y was 50. That's kind of the differences here. It's asking us, at the last part, it says, based on the estimates, which of the following is closest to the probability of the difference in proportions between a random sample of 60 doses from country X and 50 from country Y? In other words, we're going to be doing X minus Y. Let's see. Who were first married between the ages of 1834 was greater than 0.15. So really, I'm looking to find this kind of situation. If 0.15 is here, I'd like to know the probability that it's greater than that. Well, I need a distribution of x minus y. What is the mean, or in other words, what is the expected value of x minus y? It's not 0. If I wanted to find the mean of 2 different distributions, then I just find the difference of those 2 means. So 0.36 minus 0.26. I would expect the difference between the proportion between x and y to be 0.1, 10%. We now have to find, if I can find the standard deviation, this is going to be really easy. It's normal CDF of 0.151E99 with a mean of 0.1, and I don't know the standard deviation yet, but I can find it. How do you find the standard deviation of the difference of 2 populations, 2 groups? We square them and add them. But here's the kicker. I don't even have them. So we're going to find them. Remember, standard deviation of some value is equal to PQ over N. Or P hat, Q hat over N, right? So we're going to go ahead and calculate that. I'm going to do, it'll be the square root of their variances. So I'm going to square both of these. In other words, I'm not going to put the square root on them. And so it's going to be 0.36 times 0.64 divided by 60 plus 0.26 times 0.74 over 50. By the way, this formula that we're doing right now is on your formula sheet. Okay, so there's no reason you need to memorize it. It's the difference of proportions, right? And it shows you how to find that mean, the standard deviation. Turns out we're going to get, let's see, 0.08768. So 0.088 would be a rough estimate. So it turns out we're going to get 0.2843, and that's exactly answer choice B. So here, this is, again, a fairly lengthy computational question, which some people really hope for those kinds of questions. Okay? This comes from chapters 16 and chapter 6. It has lots of elements of combining distributions. We introduced that in chapter 6, but mainly the normal distribution part of that and inverse norm. I would say primarily you could probably focus on chapter 16 for this question. Okay? Question number 38. If I'm looking at this question, I instantly recognize the regression output. This is coming from chapter 27. Lin-reg T interval is what it looks like, and it definitely is. So this is your Lin-reg T interval. Remember that formula is the slope plus and minus the critical value times the standard error. Okay, and so in this case, we're looking at, I have a couple things, right? I can find the slope. So the slope here is this number right there. So I can immediately mark off the two choices for slope. The T star I can look up. We're using 95% confidence. But what's the degree of freedom for this? What's the number of my sample size? It's 11 minus 2. So we have 9 degrees of freedom. If you go back into your table and you look up that degree of freedom, you can get your critical value, your T star, is going to be equal to 2.262, which in this case eliminates answer choice A. So I'm now down to what is the margin, or I guess the last part, standard error. How did I tell you how to find standard error? Why is it easy?
It's right there.
Because it's right here. Okay? And so obviously, answer choice B, this is not even the right formula for standard error. That's S over the square root of, or like standard deviation over the square root of N. That's quantitative, single t-test or something like that. And so that's not it either. So that was really nice. If I had the slope, the T star, and the standard error, these numbers were listed there. I just had to look this one up to kind of...
You could have done it without T star.
Can you?
Well, that's what
Yeah, you can because it's just that. Good practice, though. Okay? Any questions on this one? Remember, knowing this table is important. Okay? Makes your problems a lot simpler when you get them.
I have questions.
Okay, 39. Okay, remember the power of a test is the ability to detect a false null or the ability to reject a false null. says, in this case, which of the following describes the power of the test? You want to be going, you want to determine that the null is in fact false and that you should go with the alternative. So you're looking for the patient actually has the disease. Okay? The power of the test is the ability to determine that they're not, that they actually are sick, right? And you'll find out that B, the probability that the new test indicates the patient's, that the disease in the patient's, the new test indicates the disease in a patient who has the disease. So we want that to come out to determine that they are actually sick. If it's saying that they don't have the disease, okay, then you know that, in other words, E, it wouldn't be that, and then C wouldn't be that, because they're saying that the patient doesn't have the disease, and you're concluding that they actually do, because your choice, when you talk about power, is the null is in fact a false null. Number 39 was chapter 21. This is where we talked about type 1, type 2 error, and power. And at the end, number 40, this is I guess I should back up a minute. Remember, 39 was chapter 21. Number 40, this is chapter 26. This is ChiSquared. In this case, it's asking what is the probability that the observed responses would be as far or farther from the expected response if there's no association between the groups, right? So you're using chi-square test of independence here. And so there's a number of ways I can do this. I don't have the chart and I don't have the data. That's the problem, okay? But I do have a few things. We know that chi-squared statistic was at 3.7408. And we know that we have, it's 2 rows by 3 columns, right? So 1 times 2 would equal 2 degrees of freedom. The easiest way for you to accomplish this is to go to your chi-squared chart in the back of your tables, right? You're going to go down until you find 2 degrees of freedom. You're going to go across until you find 3.7408, or as close to it as you can in your chart. Okay, and that's going to give you a thing. And you're going to look up at the top, and you're going to have it'll be between 2 p-values. And you can come over here, and you can choose between what 2 numbers would your p-value be located, and the only one that's in between those numbers is B. That's how you'd work it out. You could also use chi-squared CDF. You've never done this before, but there is a such thing, right? Chi-square CDF, you could say the lower limit is 3.4, or get ahead of myself, 7408, 1E99. The DF is equal to 2, and that would get you the same percentage. In the chart, the numbers, it's 0.15 to 0.20, and the only number that falls in between that would be answer choice B. And that concludes all of the multiple choice questions from practice test number 1.